السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last time we started to talk about Minimax. We are still in this same session of adversarial search. Inshallah, today we will focus more on how efficient Minimax is and how we make it more efficient. We just start with a quick analysis of the efficiency of Minimax, and then in the rest of the lecture and also probably the rest of the entire session, inshallah, this week and probably next week, we will focus more on how we make it more efficient. About the efficiency of the standard Minimax algorithm that we discussed last time, first let me make sure that you don't have any question about Minimax before we move forward. Any questions from your side about Minimax? So the idea is that we have turns. We have the max player who wants to maximize his benefit against the min player who wants to minimize the benefit of the other player. To evaluate the game, we go from in the search tree we go bottom up, okay, minimizing at some levels and maximizing at other levels until we reach the root. So that was the idea of Minimax. And as we saw last time, in terms of implementation, it is exactly like DFS, like depth first search. And that's why it has exactly the efficiency of DFS. So in terms of time complexity, it is order of b to the power m. B is the branching factor, how many successor states given one state, and m is the depth of the tree. Okay, so in terms of time, b to the power m. In terms of space, it is b times m. So it is efficient in terms of space, but it's not efficient, of course, in terms of time, especially if m is large. So for example, in chess, if we consider the branching factor, it's about 35. And if we look ahead 100 moves in chess, that would be really huge. Imagine will be 35 to the power 100. So that's okay. You say you don't see the screen. Just 1 second. I thought that I'm sharing. Okay, give me 1 second. Okay, you see it now, right? Yes, okay. So you didn't miss anything, don't worry. It was just one slide, the same slide. And thank you for informing me about that. As we said, for chess, the branching factor would be 35, around 35. If we look ahead 100 moves in the future, that would be a huge search tree. 35 to the power 100. That's really huge, and it's really completely infeasible. Okay, so to really play a decent game of chess, we need to do that much more efficiently. So from now, we will look into efficient ways of doing Minimax more efficiently. We assume that we have limited resources, even in either in space or in time. Usually it is time in our case, because as we said, in space the DFS is already good in terms of space complexity, but it has a problem in time complexity. It goes exponential when we go deeper. So the first idea that we will discuss, inshallah, today is called game tree pruning. If we are not able to explore the entire tree, then let's see how we can prune it. How can we cut parts of the tree so that we save time and we make the search algorithm much more efficient? So, recap of how Minimax is done. Let's say that this is the root of the tree. In DFS, we have to go left first. Then we go left again. We get a terminal node that has a value 3. 3 will be passed up. Now the value here will be 3. Then we'll continue with another terminal node. 12 will not affect this value. We'll go to the third one. 8 again will not affect this value, so 3 will be passed up. Now the value here is 3. Now we explore the second child. The second child, the first child of it, 2, so the value here is 2. Then we got 4 will not affect 2, 6 will not affect 2, so 2 will be passed up. 2 will not affect 3, so we still have 3. We'll go to the third child, and so on. So we'll have 14 here, so this will be 14. Then you got 5, then this will be 5. Then we got 2, then this will be 2. Then we have to pass back 2. Now we have 2 and 3. Of course, 3 will be the value of the game. So this is how Minimax is implemented and will be executed. Now the question is, how can we make this process more efficient? How can we make this process more efficient? Is there any branches of the tree that we can ignore and still can get the same value of the root, which is the value of the game? Or in other words, is there any values here on the leaves of the tree that if changed will not or will never affect the value that we got already at the root? Let's see here again the same example, but let's think together, what can we prune? So in the beginning we don't have anything to know, so we'll have to start with the leftmost leaf. So the leftmost leaf here we got 3, so 3 will be passed up. Now this node knows that because this is a min node, the value of that node will never be above 3, right? Because we are minimizing. So we can say that the value here is less than or equal to 3. We are guaranteed at most to get 3, but we might get even less. So can we stop here exploring the children of this node? No, we can't, because we still don't know. Maybe we can get 2 here or minus 10. Okay, so we should not stop. We should continue. Now we got 12. 12 is greater than 3, so it will not change this limit. Then we got 8. 8 again will not change anything. So now this node knows that the value of it is 3. Okay, so we'll just remove this, and 3 will be passed up here. So this node now will be the value here of that node now is 3. Now, is it greater than 3 or less than 3? This is a max node, okay? So we are maximizing. So the values here should only go up. It cannot go down because we are maximizing. So the value here will at least be 3. Okay, we never know because we didn't explore the rest of the tree yet. It might be more, but it will never be less than 3, right? Because we are maximizing. We got 3 from here. If we ever got something less than 3 from here, we will just assume that, or we will just ignore it and keep the value 3. Now, can we ignore the rest of the tree? Of course, still not, because a value here that is less than 3, or greater than 3 will change the value of the root, so we cannot stop. So we'll have to continue. So the leftmost child of this is 2. Now 2 will be passed up. Now this value, okay, because this is a min node, will be at most 2. It can go down, but it cannot go up. I mean, it can decrease, but it cannot decrease. It can decrease, but it cannot increase because we are minimizing. Okay, so whatever value from here can be less than 2, right? Or can be more, but the value of that node will never be above 2. Now, since we got this has to be less than or equal to 2. Now, this is guaranteed to have 3 at least. Okay, so any value here, any value in this subtree that we will get here will never be more than 2, right? We'll never make this value more than 2. And thus, will never change the value here because we are guaranteed 3. Okay, that means that we should cut here. We should cut here. We should prune at that point. We don't need to look at the subtree here at all, even if this is very huge, even if this is very deep. Okay, any value here will never change the value of the root at all, because now we are guaranteed at least 3. This one is guaranteed at most 2, so we'll never go above 2, and thus will never change the value that we have here, because it's less than what is guaranteed already. So we can prune safely this subtree. Now, should we say that now the value of this root is 3 and we are done? Of course not. We have to still explore this branch. So we'll continue with this branch because we might get better than 3. We cannot get better than 3 from this branch now, right? But we might get something from here. So we'll start with the leftmost one. This is 14. So now this value is less than or equal to 14. Should we stop now? Of course not. Why not? Because we might get, for example, yes, we might change this value. Maybe you can get 10 here, and in that case, we change this to 10, and eventually we might get 10 from that branch and change this value. So we cannot stop. We cannot stop. Okay, so we have to continue with the second child. Now this value is 5. Okay, we are minimizing, so this value will change to 5. Okay, now should we go to the third child? Yes, we should. Okay, yes, we should. We cannot just stop and say we will not get anything from here. If that one is 4, then this one will be 4, and then this one will be 4. So it will change the value that we have here. So we will have to continue with that child. Now we got 2. This one will be 2. 2 will be passed up, and of course 2 is less than 3. So the value of this will be 3 eventually. Okay, so the value of the game will be 3. And we managed to prune part of the tree. Of course, this because of the simplicity of this example, we didn't prune much, but in larger example, we might prune more. Okay, so that's the idea. We should prune at the point where we will never change from that branch down. We will never be able to change the value of the game, which is the value of the root. Okay, if that's the case, then we should stop at that branch, ignoring the entire subtree rooted at that branch, and continue in the rest of the tree. Of course, pruning here will save time. Any question about this? Is that clear? Is that not clear? Okay, good. So let's try to generalize this idea. So this idea is generalized in what we call alpha beta pruning. So actually we can do this pruning on min nodes and max nodes. That's why we have 2 values here, alpha and beta. So what is the general idea? Let's say that we have a min node here, this one, okay, and the value of this min node is n. The value of this min node is 10. Let's say that this is n. Let's say that this value is 9. So n is 9. And along the path from that node to the root, there is a max node that has a value a at least. So this, if we got this from a child here, that means that this value is at least a. And because this is the main value, also this value is at least is at most 9, because we are still exploring here. Okay, so this value is at least 9. This value is at least a, and let's assume that a here let's assume that that a here is 12. Okay, so that means that the value of this node will never be above 9, so it will only decrease over time. the value here will never be beyond 12. It will only increase. So that means that this branch will never be explored because it's a bad option for this node. This node will never go to this branch anyway because it will get a value that is less than the value that is already guaranteed. Okay, we call this value the alpha value. So the main node always, while it's exploring its children, it keeps an eye on the best option for the max nodes on the path from that node to the root. We call that alpha. If the value that I got so far is less than alpha, that means that what I'm doing here will never be explored because it's a bad option with respect to the max node above me. So I should stop and prune at that point. The whole subtree here should be pruned, should not be explored at all, and I should pass back whatever value that I got so far, which is n, which is 9 here, because even if I got less than 9 from that subtree, will never affect the value that we have here. Similarly, we can do that with a max node with a beta value, but it's symmetric. Okay, so in this case, we'll say that if my value is greater than beta, which is the best option for a min node, then I should prune at that point. I should not continue exploring my children. So that's the general idea of alpha beta pruning. Let's do a quiz, actually 2 examples on alpha beta pruning, just to make sure that the concept is clear before we actually see the pseudocode for the implementation. I will give you about let's say 30 seconds here. I have 2 questions here on this example. One, what is the value of the game? Second, what should we prune here if we do alpha beta pruning? What branches we should completely ignore in exploring this search tree? And raise your hand please if you are ready to answer. Okay, we'll wait for some time. So Yusuf, are you ready? Yusuf? Okay, Yusuf, I was asking if we need actually to do alpha beta pruning to get the value of the game. So the value of the game here is 8, right? Do we need to do any pruning to get this value, or we can just run Minimax? No, I'm not talking about pruning now. I'm just asking, if I asked you only to give me the value of the game, do you have to do pruning? No, right? We can just run Minimax. Okay, actually pruning will not affect the value of the game. Okay, pruning will not affect the value of the game. Okay, now let's do together. Let's see if we can do pruning. So Yusuf, we have to explore, of course, this 10, right? And do we have to explore also this 8? Okay. So step by step, Yusuf, you are ahead of me. So we'll pass up 8. So now we have greater than or equal to 8 here. Okay. Type. Now should we prune D? No. We have to. Yeah, we might get something above 8, right? So we have to continue D. Should we prune E? No. So we have to pass up. Yeah. So this one now will be less than or equal to 4. Now at that point, should we prune? We should prune F. Yeah, why? Why is that? Yes, so the alpha value now is 8, okay, and our value now is less than alpha. So this value, as time goes, will only decrease, okay? and thus we cannot change this 8 at all. So this branch, even if we don't have any one node here, if we have huge subtree here, the whole thing will be pruned and will not need to explore this branch. Thanks, Yusuf. Okay, now we will switch to the second example. I will give you 1 minute to think about this. Again, 2 questions. What is the value of the game? And second, what should we prune? Raise your hand, please, if you have the answer. Give you some more time. Okay, Faisal. Yes, as you see here, yes. Where يا فيصل؟ واحدة بس عليا. You mean from the bottom? Okay, from the left we will get 10, then 100, 2, 20, then here, okay, and 10. Okay, so 10 is the value of the game. Any objection from anyone? Okay, and again, we don't, of course, need to do any pruning to get the value of the game. So I will raise anything, and Faisal, stay with me, please. Now, Faisal, what branches we should prune? Okay, so you will not tell me now. You want to do it with me step by step. I will do it anyway, step by step. Okay, so let's do it from the beginning. Should we go A, B, C? Yes, we will always have that, right? Because we don't have any information, we cannot just prune from the beginning. We have to get some information. So we have 10 here. So 10 will be up. So this one will be less than or equal to, greater than or equal to 10, right? Then we have 6. Okay, so 6 will not change anything here. So the value here will be 10. So 10 will be passed up. So now this one will be less than or equal to 10 or greater than or equal to 10. Less than or equal to 10, yes, because that's minimum. So less than or equal to 10. Now, should we go to E? Yes. Should we go to F? Yes. Okay, so we'll have 100 here. Sorry, what are you saying, Faisal? Yes. Yes. So now this one will be at least 100. Okay, should we go to G? Whoa, no, why not? Yes. Yes, so the beta value here is 10. The value that we got here is 100. We will never get beyond 100, and thus we'll never change this because that's at most 10. Okay, so any value here from that branch, any value that we will get here will not change the value of this node. Okay, so we will just stop here and we'll just assume that the value of this node is 100. Okay, and we'll pass it up. Of course, 100 will not change anything here, so the value here will be 10, right? So just ignore this, remove this, and pass 10 up to the root. Now the root has less than or equal to or greater than or equal to? Greater than or equal to 10. Very good. Now should we go to H? Okay, then to J. Now this will be up Now we got greater than or equal to 1. Okay, should we stop? No, because we might get greater than 1, which might be 100, for example. Maybe it will be good. So we'll have to go to k. K will give me 2, so this node now is 2, right? The value of this node now is 2, so I should pass it up. Now this will be less than or equal to 2. Should we do any pruning now? We should continue with L. Yes. So always check the path to the root, and if that's min node, check the values of the max nodes. If I ever have a value here that is greater than the value that I have, which is the case, then I should stop. Why is that? Because I will never get from the whole subtree here, I will never get a value that is greater than 2, which means that I will never pass up a value that will affect the value of the root. Okay, so whatever the values here will not be greater than 2. I mean, it will not make the value of that node greater than 2, and thus will not affect the value of that node. So we should prune here. So this entire branch, this entire subtree will be pruned, will not be explored completely, and the value of that node will be considered 2, although it might be less, by the way, right? And in reality, it might be less. In this case, it's not, but in reality, it might be less. We might get minus 1,000, for example, right? But still, whatever value we'll get here will not change the value of the root. So we'll assume that it is 2. This 2 will be passed up, and eventually the value of the game now is 10, which is the same value we got in the beginning. Thanks, Faisal. Any questions about alpha beta pruning? I see Saad and Abdurrahman raising hands. Are these questions, or you were trying to answer before? Okay, so Abdurrahman, so okay, so lower your hand then. Okay, Saad. Yes. Yes. And when we are in the main nodes, we check the alpha values of the max nodes on my path to the root. Okay, and if my value is less than the alpha value, then we should stop. On the other hand, similar we can do to the max nodes, but the opposite case. Okay. Any other questions? Everything is clear? I might need to ask you from time to time if you hear me. Okay, do you hear me? Yes, okay. Okay, so let's continue then. This is the pseudocode for alpha beta implementation. So as I just mentioned to Saad, if we have the main value case, then we get alpha and beta values from the parent. Of course, remember that this is again DFS, still DFS, but with pruning. So when we use DFS, we always get code from the parent. So the state now will go from that current state to every successor. Okay, and because this is the main value node, so we will minimize whatever value we'll get from the successor. But notice that we push alpha and beta to the successors. Okay, so to my children, I push alpha and beta. Now, if the value that I get is less than alpha, what is alpha? Alpha is the max best option on path to the root. So from my node to the root of the tree, what is the best option the max got? That's alpha. If I ever got a value here that is less than alpha, that means that this path is not worthwhile, is not worth exploring. Okay, I have, the root has better options. Okay, so this path will never be explored, so it deserves to be pruned. It deserves to be cut from the search tree. So I should not continue with the other children. I should immediately return my value. Okay, and if that's not the case, then I should update also beta so that I can push it to the rest of my subtree. Similarly, for the max value, here I'm maximizing my value. If my value is ever greater than beta, which is the best option for the main nodes on my path to the root, then I should stop and return v. Now v might not be the exact value of my state, but still it is good enough for the root to know that this path is bad. Okay, and also similarly I update the value alpha so that I can push it to my successors, my subtree. Okay, question Abdurrahman. Yes, yes, still we are assuming it's optimal, yes. Are you saying that human is not smart? Okay, we'll talk about that inshallah after this session, inshallah. I mean, probably this week we will start talking about uncertainty, inshallah. Okay. But so far, yes, we are assuming that we are playing an optimal player, playing against an optimal player. Any other questions? Mustafa? It is done recursively. Yeah, you're welcome. Any other questions? Okay, now let's continue and talk about some properties of alpha beta pruning. The first one is that the pruning has no effect on minimax value computed at the root, and we actually talked about that before. Whatever pruning that we are doing will not affect, of course, that's the concept, the core concept of alpha beta pruning, that whatever pruning is doing will not affect the value of the game, the value of the root. Okay, it will just save us time without changing the value of the root. Okay, so this is the first thing. There is no effect on the minimax value computed for the root. The second thing is that the values of the intermediate nodes might be wrong. And to understand this, let's look at the example here. Okay, let's look at the example here. Now, the value of the game here, to evaluate it, this is 10, and this is 0, and that maximum, that should be 10. So the value of this game is 10. Okay, now let's see if we can do any pruning. So we'll start with here, this 10 will be passed, so this will be 10, will be passed here, that will be at least 10. Okay, now we go to the right branch, and then go here, this 10 will be passed up, now we get less than or equal to 10. Okay, remember here, we had if v is less than or equal to alpha, we will stop and we will return the value that we got. So in this example, we'll just prune here. We'll not look at this terminal node. Even if we have a subtree here, will be just ignored. Okay, so we will not look at this 0. We'll actually, once we get this 10 and we compare this 10 with the alpha here, which is 10 here, then we will stop. We'll pass up 10. So we'll assume that we have 10 here, although the actual value here is 0. Okay, the actual value here is 0 because the minimum is 0. But we will not care about that. We care only about the root value, and the root value will be correct, of course, will be eventually 10. Okay, so two things here. The root value is the same, is accurate, but the value of the children or the non-terminal nodes might not be correct. Actually, in this case, it won't be correct. Type, why is that a problem? We care about the root, right? So the value of the root is good, is correct. We care about the values of the non-terminal nodes, especially when we have a tie like that. Yani, if now you look at the tree after pruning, you have 10 here and you have 10 here. Which branch this player will take? Which decision now this player will take? Left or right? Both are the same, right? Both are the same value. In reality, they are not. One is 10 and one is 0. But because we did pruning, a side effect of pruning here is that we have now a value that is not correct. Okay? So, to solve this issue, we have multiple ways. One way is to always keep the value of the, if we, in case of ties like that, we always go to the first branch that got this value, because it will always be the case that the first branch we visit has a correct value. Okay, so in this case we will take the left decision, or implement this without the equality. Okay, so here you see here there is an equality, here there is an equality. Okay, so make it just inequality. So prune only if we are strictly less than alpha, or if we are strictly above beta. In this case, we will never have ties. Okay, and we will not have this problem. Or a third way is to rerun the algorithm at the children to get the exact value at each of the children. Of course, this is an overhead. Okay, so there are multiple ways. Maybe the best of them, or the most efficient one of them, is to just keep track of the first time you got a value, so that will be the correct value. So this is one issue. Another issue that we want to talk about, and we'll continue talking about inshallah later, probably this week or next week, is the ordering of the children. If we started with a child that has bad option, then we will prune early, and pruning early will save time. So the order of the children will have an effect of the efficiency or the time that is needed for pruning. If we assume that we got perfect ordering here, and we'll talk about, as I said, ordering later inshallah, let's assume that we got perfect ordering. For that case, time complexity can drop to b to the power m divided by 2. Compare that to b to the power m. Okay, that's a huge saving. The exponent here is divided by 2. So this is like saving half of the depth that we would have explored before. That's a huge saving. Okay, so double saved depth. Okay, but still playing chess with that will be hopeless. Still, the size of the tree will be huge, and it will be infeasible to play a decent chess game, even with the perfect ordering. So that means that we need still more ways of efficient processing of the tree, so that we can feasibly play a decent chess game. Also, this saving, okay, doesn't mean that we will save only time, but even if we have time, that means that we can explore more depth. Yani, if I have time budget to explore depth 10, now by that saving I can explore depth 20. Okay, because it will take the same time like without a perfect ordering. The last point that I want to say here about alpha beta pruning is that alpha beta pruning is an example of what we call meta reasoning. What is meta reasoning? Meta reasoning is about doing computation to save us more computations in the future. يعني alpha beta pruning, if you look at it, it is an overhead over the classical Minimax algorithm, right? We can just remove the alpha and beta and just explore Minimax algorithm as before. But keeping track of the alpha and beta values is an overhead. So it's more computations that we are doing than the standard one. But we are doing these computations so that we save computations in the future. This is what we mean by meta reasoning. Computing about what to compute, or computing about what not to compute, or to avoid compute in the future. With that, I think we reached the end of the slides. Of course, we lost some time with this audio issue, but I think we are okay. We are done with the slides 5.A. Inshallah, next time we will start to think about more ways of doing efficient processing for the Minimax search tree. Okay, so we'll stop here inshallah and talk to you on Tuesday. We will have a quiz on Tuesday, and the quiz on Tuesday will cover up to this point. Okay, so up to the end of slides 5.A, if that was your question, Ya Abdurrahman. Any other questions? Mustafa? Yes, yes, of course. It will be order b to the power m. Yes, of course, it will take a lot of time. As we said, if you do the ordering perfectly, you will have less the depth, which is much less than half the time, by the way, because as you go down in the tree, you get exponential increase in the number of nodes. So that's actually saving a lot. Yes. You're welcome. You're welcome. Any other questions? Okay, Hamza? Yes. No. Why are you saying that? Well, you were with us since the beginning, Hamza. Did you see this example? Okay, so for this, for this example, we tuned, right? We pruned this complete part of the tree without looking at it at all. So that will save time, right? Did you get it now? Okay. Any other questions? Okay, inshallah, talk to you on Tuesday. Assalamu alaikum wa rahmatullahi wa barakatuh.